And now we will hear Rutger talk about the semantics of Nix.
Right, I hope I'm audible. Okay, so I'd like to start with a proposition, namely that having the formal semantics for a programming language is quite awesome, and because we can do multiple things with this kind of stuff. Because we can be extremely precise about what the language actually means. So we can do stuff like creating program logics, we can verify compilers if we have multiple implementations of the same language. We can make sure they agree, or stuff like static analysis tools. We can verify that they are correct. Now if we give a kind of executable semantics, then if we have some kind of a test suite for the language, or we want to test this on some example programs, then this becomes quite easy. Or if we have a reference interpreter, then we can also do that kind of stuff. Now if we have a proof assistant that we actually make use of to mechanize the semantics, then we can also do stuff like verifying, for example, this reference interpreter. So we can reuse this very easily. Now this is kind of stuff has been done before, so think of CompSert, this kind of stuff. Today we won't be looking at any common language like C, we'll be looking at a kind of weird language, Nix. And we'll get to why in just a second. We'll be discussing two kinds of semantics because they're good for different kinds of things. So substitution-based operational semantics, that's nice for creating stuff like program logics. It's concise, readable, but quite inefficient. You wouldn't want to actually execute any kind of a program with this because your terms tend to blow up a bit. So environment-based interpreters are better for this, they're nice for testing, and they're relatively efficient, but they're not nice for reasoning with. So we'll be discussing these two perspectives today. So first we'll talk about what Nix even is for the ones that don't know. Then we'll be discussing why Nix, and then about how we went about creating these kinds of semantics. So what is Nix? It's primarily a package manager that has this kind of purely functional aspect to it. So whenever you have a package, you kind of pin all of the dependencies, and the idea is that the build process is sufficiently isolated that you always get the same kind of result. Ideally, you get this kind of binary reproducibility where you always get exactly the same output. And now NixOS is a distribution that's based on the package manager, where you can have declarative kind of configuration, and at the heart of all of this is the Nix expression language. And you can see here on the side that you have an example package. This is for the OwnTracks recorder, and this is what the Nix expression language looks like. So this is what we'll be discussing today. So I want to just give a quick overview of what this language looks like. It's functional, lazy, and untyped. So in some sense, it's a bit similar to Haskell, just without the types and a bit different. So lambda abstractions, they have this syntax. That's a good one to remember. You'll be seeing it a lot. And Nix is lazy. So for example, we have big omega there, but since it's not used after the let, this program doesn't actually loop. Now let bindings are also mutually recursive, so we can define the Fibonacci function just like that. Now there's also attribute sets in Nix, and these appear everywhere. So you could also see them in an example before. And these also allow recursivity, mutual recursion between the different bindings of the attribute set. So for example, the Fibonacci function can also be defined inside of a recursive attribute set, and then we can call it by selecting it from the attribute set. So that's just like a JSON dictionary, but with code. Now there's more kind of interesting or weirdish features of attribute sets. So if you add an underscore functor attribute, then all of a sudden the attribute set itself can be called. And then the first argument to this underscore functor thing, when it gets called, is the attribute set itself. So that's how this again turns into Fibonacci function. There's more interesting stuff. So Nix has dynamic binding. This is something that we'll be focusing on the next few slides. And then there's also different evaluation strategies using sec and deep sec. So I just want to have you think about the following programs, about whether they are well scoped or not. So Nix has this with construct. It takes an attribute set, and then it makes all of those available in the second argument to the with construct after the semicolon. So in this case, we see that x and y are defined in the attribute set, so clearly they will be available on the right-hand side. So this program is indeed well scoped. But for example, we can also kind of extract this attribute set and then bind it to some variable and then use that with the with. But this is, of course, still well scoped. That seems just fine. But note that this can be any expression. With is not syntactic sugar. So if we have some kind of a let binding that calls some function that generates some, presumably an attribute set, then of course it's not clear anymore whether x and y will be bound. So we'll have to say, maybe. We don't know if this program is closed. Now, shadowing behavior in Nix is also a bit weird. So for example, well, let works just like you would expect it to. Let returns 12. But if we have, well, if we have 2 times with, then things get a little bit tricky, but this still works the way you would expect it to. So that's also good. But if you have a let first and then a with afterwards, then all of a sudden you'll notice that let takes priority over with. This is a bit weird. Now the other way around, this still works the way that you would expect it to. Now if you take this in the context of the Nix package manager, then this makes some sense, but I won't go into detail about why. Now, one more thing that I want to mention about the semantics of Nix is these different evaluation strategies. So normally if we have big omega, this term that has no normal form, then if this is just in the let binding that's unused, then this of course still returns through this program. Now if we have sec, then the first argument gets evaluated to weak hat normal form before the second argument is returned, but of course this loops because big omega loops. But if we put it inside of a list, then again, Nix is lazy, so the elements of the list don't get evaluated, so this just returns true. Now with deepsec, this kind of evaluation is done recursively, so this loops, because omega loops. But if we have 2 attributes, x and y, well, in this case, y should crash, because this is an invalid application. So the question is kind of, what does this program do? Does it crash, or does it loop? And in this case, well, it depends. Because in the case of Nix, it does not by default evaluate stuff on an alphabetical order. This kind of depends on the order that the different names basically like appeared first to the interpreter. So this is weird. But anyway, that's a nice challenge to formalize. There's one more reason why it makes sense to give a formal semantics for Nix. So this has been kind of done before by the original author of Nix, Ilko Dolstra. He has written down some formal semantics, but these are a bit lacking, so they are not tested, not complete, and such. And there's also a case where the semantics for the with statement are not very precisely specified, which makes the substitution kind of go wrong. So this is done naively, but that causes the shadowing for with to not work properly. Now, as of 2025, there's also a decent selection of Nix implementations that you can choose from, but I'm not aware of any common specification for the language. So it might be time for something like this. Now that we've seen all of these peculiarities with shadowing, this with construct, we might be wondering, okay, so how do we even start to define a substitution-based operational semantics? Now you might say, okay, just use something like the Brown indices or whatever, but this doesn't work for Nix because names are relevant, as we saw before. So we wouldn't know what the Brown indices to assign to x and y here. So you might say, well, just use strings, but strings are really annoying because you have to do stuff like alpha conversion, and we want to do stuff in rock, and alpha conversion in rock is hell. So we want to do something else. And what we came up with is some form of deferred substitution, which is still pretty concise. You don't really get capture problems. And even when you reduce open programs, this still works the way you would expect it to, so we don't get this kind of weird behavior. And this scales to the with construct in Nix, also dynamic variable lookup, and also constructs like eval, even though Nix doesn't have those. Now just to illustrate, I want to quickly discuss the call by name lambda calculus and show you that when we handle an open program in here, then this goes wrong. So for example, you see that y is unbound at the top level here. We reduce by 1 step, and then all of a sudden it becomes bound because it's substituted into this lambda abstraction. And if we take one more step, we get this string a, but that's really not the result we want. So of course we can do alpha conversion, but again, like I mentioned, alpha conversion is really annoying. So what we do is the following. You might be familiar with explicit substitution. We can do this in a kind of way that we still preserve names. And what we do is we kind of push through these explicit substitutions and we just reify them at the variable level. So there's this association list of variable names to expressions that we associate with the variable name. But you might say, okay, but this is dumb. We already know the variable name. Why would you associate all of the possible substitutions with this? And I would say, well, you're right about that. Can be simpler. So we can do one of two things, right? So we can just say that there's an optional substitution that we associate with a variable. So if there's none, then this is just a plain variable, and we'll often just write it x instead of x none. Or there's this deferred substitution e that we associate with the variable, and at the point that this variable then appears at the top level, so that when there's no binders around it anymore, then we can reduce this to the deferred substitution itself. We can also choose to generalize instead and have the variable names or even the binder names for the lambda abstractions computed dynamically, but if you want to know more about this, I would suggest you to read the paper. There's also one more strategy that I would just like to honorably mention. This is by Ben Lipmeyer. He revised the substitution at the lambda abstraction level, but it's not clear to us if this scales to the next features that we want to implement in our operational semantics. So just one more time to make this a bit clear how this works. If we have this deferred substitution associated to a variable at the top level, then we can reduce this to the deferred substitution itself. And all of these rules, we only reapply them at the top level, which makes sure that we don't actually get any kind of capture problems. And important to note is that the substitution function always allows this deferred substitution to be overwritten. This is a pretty core piece of this and why it actually works. So let's look at this counterexample from just before again and use deferred substitutions instead. So you see this y here, you should read that as y none. Seems to be working. Okay. I hope I'm audible again. Okay, so I guess you've had some time to read this now, and this should be pretty obvious to you at this point. When we reduce this, then we don't substitute inside of the deferred substitution, so we don't actually get capture. So when we reduce here, then we get y as a result, which is exactly what we want, because we do not want this program to actually evaluate correctly, or we don't want it to evaluate to a value at least. So this is a better result. Now we do multiple things in our paper. So we have multiple interpreters, and for all of these interpreters, we have this kind of a lemma. So the interpreter that we define is sounding complete with regard to the operational semantics with deferred substitutions for terminating programs, faulty programs, and diverging programs. And this all holds for open terms. You might also want to note that for the interpreter, there's this environment associated with this. That's the empty set in all of these cases, because we are considering normal programs that are yeah. Okay, so now we have seen all of this kind of stuff, and you might be wondering how does this all transfer to Nix? Because Nix has this weird shadowing stuff. You've talked about the closed terms, but not about the weird shadowing stuff that's going on with the width. So we do this by extending the deferred substitutions a little bit and basically assigning a kind of binding kind with the deferred substitution. So this means, so we adjust the substitution function so that basically whenever we want to substitute for a variable again, and it has a stronger kind, so the abs kind, then we can override it. But if it has the width kind, then it is not overwritten. So you can also kind of see this below, that we have this abstraction kind. That's what's generated by the let, because it has the same strength as a lambda abstraction that's associated with the substitution. So we get the kind of shadowing behavior that we would expect. Now, just to intimidate you a little bit, this is the entire grammar of our core Nix language. So some interesting things to highlight are the following. This is how we define recursive, or how we define attribute sets. All of the attributes have a separate recursivity instead of the attribute set as a whole, because this is much more convenient. Dosser also does this in his earlier semantics. We have pattern matching lambdas. If you want to know what these are, I have a backup slide for perhaps a question. Then there's the sequencing construct, so deep sec and just normal shallow sec. And we also support IEEE floating point numbers using the flock library for rock. Now all of this, we have a front end for this. So there's the interpreter that we've written and verified in rock. and it takes this kind of core Nix expression and translates it to a value. And we have an OCaml frontend which basically parses Nix code, elaborates it to the core language, and then gives this result. So we pass a decent amount of language tests, although definitely not all of them apply. A decent amount of language tests are also simply not interesting to us because we don't consider the package management aspect of Nix, or we don't really care about XML encoding and this kind of stuff, which Nix does support. Now we don't agree on all tests. There's still some which we don't pass because our interpreter is, as I mentioned, call by name, but Nix is lazy, so we can't detect cycles, for example, in some cases. So just to conclude, what we've contributed are the following. We give a form of deferred substitutions that also scales to dynamic and scripting languages like Nix. We prove the soundness and completeness of environment-based interpreters with regard to these kinds of deferred substitution-based operational semantics. And we give the most comprehensive semantics of Nix to date, as far as we know, which is evaluated on the Nix language tests. That's it. Thank you very much.
I will start. So, like, given the title of the session about separation logic, do you plan to have like a logic for Nix, or?
So we have defined a small program logic for this, a weakest precondition-based logic, and we've done some simple proofs in Rock for this as well. But we didn't create any kind of tactic support, so this was still quite cumbersome. But it is possible to do this kind of stuff, yeah.
So I was curious about this comment you made at the end. Do you foresee any issues with combining laziness with the deferred substitutions that you've shown so far? Or fundamentally, is there another reason why your calculus is called by name? There are lazy calculi out there.
I don't think that there should necessarily be any issues, or I can't come up with any immediately. But in general, defining a lazy operational semantics is a bit annoying. So defining a lazy interpreter, I think, is quite a bit easier. As far as I know, there's currently a student of Robbert who's working on this. But I, in general, don't know if it makes that much sense. Although I guess if you really want to match the Nix interpreter as it exists today in your operational semantics, you would have to define it in a kind of lazy way. Because Nix does like weird pointer equality kind of stuff when comparing stuff. So if you want to get this exactly right, or at least if you would take the official Nix interpreter to be like the semantics, then yeah, you would have to, I guess, do a lazy operational semantics. So it might be quite tricky, yeah.
Yeah, thank you.
Hi, thanks for the talk. It seems like the with statement caused you a lot of trouble, and I think other Nix alternatives out there have had similar issues, like Nickel. Do you think the language really needs this feature, or is it just to be interoperable that you're, yeah?
I don't necessarily want to rate the features of Nix, but with is definitely a bit weird. And I believe that Nickel indeed also doesn't have this feature, but somehow this still seems to be fine. I believe that there's other ways to get similar kinds of constructs which have similar nice properties, so you can like bring all packages into scope, so you don't have to prefix these with packages dot or whatever. So I think that there might be nicer solutions than with, because for example, JavaScript also has with, but not strict JavaScript, which everyone is supposed to use now. So it's also kind of been banished from there. So yeah.
Right. Thanks.
Thank you for the talk. I think this is really cool. I guess one of the interesting things about Nix is how much of like the tooling in the ecosystem is in the language itself, and so even just verifying these core aspects of the language is useful. But at the end of the day, because Nix is still predominantly uses a build system and everything comes down to the derivations. And I know you said you weren't interested in doing that because you were interested in like these aspects of the language. But what do you think the approach would be for wanting to have like a complete verification of Nix, including the build system?
That's a good question, and I haven't given too much thought to this yet, but I think it would get very complicated very quickly, or you would have to, I guess you would need some kind of a way to like interface with the outside world, because Nix has stuff where you can, like, for example, I don't know, fetch a Git repository, or fetch some kind, you have like these built-in functions like fetch URL.
Yeah, it has a lot of built-ins that have I/O, like not pleasant I/O, basically.
Right, so there's like some I/O going on, although I guess in Nix you always indicate hashes, so then this is still, in a way, always going to give you the same result, or at least as long as it like successfully executes, then it's going to give you the same result. So that's at least one nice aspect of this, but I'm not sure what the value is in defining the semantics of the build system itself. Yeah.
Okay, thank you.
Maybe it could give you an idea. Like there was a project to kind of do like static analysis on the Debian scripts, like install scripts, and then like model checking to check that the scripts would install properly and so on. So like there is previous work on build, install stuff. Yes, I guess like what are your next steps in general for this?
For now, there's no plans for next steps. This is not part of a PhD or something. I'm a master's student, so there's no planned future work, but who knows what the future will bring.
Okay, thank you. So let's thank the speaker again.